Hello and welcome everyone to the Varsity Tutors StarCourse series, where today we're going to put an extra emphasis on that star. We've always known that you're superstars, and today we're going to look back to the universe's earliest stars to prove that you're superstars, and we have the absolute best teacher to help us do that. You know her as the physics girl from YouTube. It's Dianna Cowern, who's going to teach us why that's true and show us how we know that with some proof and some fun demonstrations along the way. So be ready to keep it interactive. Be ready to get up and move around. Got a couple things you should know before we get started. One, you should see a chat box to the right of the screen here that we're talking to you on. Diana's going to ask you a lot of questions to find out what you know and think about some of the universe's earliest origins and where we all came from. So use that area to answer her questions whenever she asks, and also ask as many questions as you want. Ask any questions you have throughout today's session. In the last 10 minutes, I'm going to interview Dianna to get you as many answers as we can. So don't wait for a dedicated time. Ask questions as you have them, and we'll get them all as we go. Also, make sure you've got a camera nearby, because in about 35 minutes, we're going to give everybody a chance to lean into the screen, take a selfie with Dianna and that really cool cat there, but she'll explain a little bit more before. That's actually part of a prize package for you. If you upload your photo to Instagram, tag Varsity Tutors, and the physics girl will have the official handles up on the way out. You'll be entered to win a spot in a Varsity Tutors after school club, plus that cool stuffed cat there, Schrodinger's cat, which again, you'll learn about more soon. But first, we've got to learn about why you're a superstar and how we know it. So let me introduce you to your teacher for today, Dianna Cowern.
Hello, everyone. I'm so excited. Thank you so much for that intro, Brian. I'm really excited to be here with you guys today. Wherever you are on your couch or sitting at your desk. I'm here in San Diego, and with me in the studio here, this is where I typically work and make my videos. But in here with me today is Levi, who's behind the camera. He's usually editing all of my YouTube videos, but today he's helping make sure everything goes smoothly for us. We're going to have so much fun. We're going to leave the planet today. We're going to get to head into outer space with our minds and get to think about space and some of the big crazy ideas like stars and time machines and the whole universe. And in case you didn't hear, this class is super friendly for all ages. So if you've got like a little sister or a cousin in the house with you and they're not sitting with you, feel free to bring them on in, because we're going to talk about my favorite topic today, which is astronomy, because that's what I used to do as a scientist. I used to study astronomy. So let's get started. I have a question for you to start off the lesson. Here's my question. Using a big ball, a small ball, a thunderstorm, I've got some special effects, thank you, Levi, and some triangles and a rainbow, I'm going to prove to you that your family tree includes a star way bigger than the sun. A star way bigger than the sun. What do you think of that? Do you think that you're crazy? I thought you were a scientist. What are you talking about here? Or do you think, B, you're crazy, but I want to see where you're going with this? Or do you think, C, I believe you, but I want to see some proof of what you're talking about? Or do you think, D, yawn, I already knew that. What else have you got for me? What do you think about this crazy idea that your family tree includes a star way bigger than the sun? I see some C's coming in, which is that you believe me, but you want to see the proof, which is awesome, because that's exactly what we're going to do today. Not many D's, but a couple of you want to see what I got. So hopefully I'll have something exciting for you guys in there too. And then a bunch of A's and B's that you think I'm crazy. If you're one of those answers that you chose A and B, and you think I'm crazy, just wait until I tell you that the room you're in acts like a time machine. Let's see what that means. Let's jump right into that. I've got another question for you to lead into the time machine. So here's another question. How can you tell how far away lightning is during a thunderstorm? So you're sitting there during a thunderstorm and you're seeing the flashes of lightning and hearing the thunder. How can you tell how far away that lightning is when you're seeing it and hearing it? Do you think you know, Levi? You know the answer to this one? Yeah? You remember this one? Okay. I'm seeing some awesome answers. One, I don't know. That's totally fair. You measure it. That's a That's a great question. I want to know a little more detail. You count the seconds between lightning and thunder. Okay, we're getting a little closer. A second per mile, so count the number of seconds. Yeah, something similar answers like that. Check your weather app. I like that. Okay, so it seems like a lot of you have heard this method that I've always heard, that I learned in school, which is that you count the seconds between when you see the lightning and when you hear the thunder, and that tells you the number of miles. It's not completely precise, but it actually is very close. And I'm going to tell you the exact number. But I have one more follow-up question before we get to that. When a big event happens, like we're talking like a lightning strike or a firework, something like that, do you see it first, or do you hear it first, or do you see it and hear it at the same exact time? Do you see it first? Do you hear it first? Or do you see it and hear it at the same exact time? This is definitely related to the last question. So if you got the last one, then you probably know the answer to this one as well. Okay, I'm seeing a mix. Most of you are saying that you see it first. A couple have said that you hear it first. And some of you guys are saying you see and hear it at the same time. So yeah, awesome. I'm seeing some good answers come in. The answer is, a lot of you are right. So I'm good, you're on the right track. The answer is that you see it first. You see the lightning first before you hear it. Why do you see it first? Well, seeing means that the light got to you from the lightning. That's why we call it lightning. And then hearing means that the sound reached you. The sound, we call that the thunder. So the sound from the lightning reached you, which means that the light got to you first if you can see it first. And that makes total sense, because the fact is that light travels faster than sound. That's why you can count the seconds between, this is what we were talking in the first question. You can count the seconds between the seeing the lightning and hearing it, because the lightning actually gets to you in a fraction of a second. But the thunder, that sound, takes longer. So the bigger the distance between you and the lightning, the bigger the time gap is going to be. So I told you I'd say the exact numbers. If the lightning is 1 mile away, then the sound is going to take you 5 seconds to get to you. It's actually 4.8 to be precise. But if you count about 5 seconds, then the lightning is about 1 mile away from you. So it's pretty cool that it works out to be almost that perfect. So you're there, you see the lightning, you count 1, 2, 3. If you get to 5, the lightning is 1 mile away. If you get to 10 seconds, then the lightning is 2 miles away, and so forth. If you see and hear the lightning at the exact same time, definitely take cover, get inside, because that means the lightning is right on top of you. And we might have to wake you up from when the lightning hit your house. Hopefully that never happens. So the light is so fast that it gets to you in way less than a second. It's immediate. And then the thunder has a bit of a delay, which is why you can count between seeing and hearing. Another example of this whole thing, the difference between lightning and thunder, the difference between the sound and the light that gets to you, is with echoes. So if you've ever gone to a canyon, you've ever gone hiking, you've probably never brought a laser pointer with you. But if you did, and you shot the laser pointer at the, I don't know if you guys can see this back there on there, but if you turn on the laser pointer and you yell laser at the exact same time, then you're going to see the laser pointer immediately. You're going to see it on the other side of the canyon immediately, but you're going to hear something like laser, 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 laser. 1 second, 2 seconds, 3 seconds later. But most importantly, this means that both light and sound have to travel to you. So even though there's a difference in the time it takes, the speed, they both do have to travel. I'm going to show you that with a little example, and I want you to try this with me. So if you can get up where you are, I'm going to have us all run across the room. So I'm actually going to go off screen for a second, or out of frame for a second, and I'm going to run across the office in here, and I'm going to time how long it takes me to go from one side of my office to the other and back. So I want you to do the same thing. If you're too comfortable, Totally fine. Just imagine yourself running across your room and back. But I want you to count how many seconds it takes you. I'm going to count us all down from 3, 3, 2, 1, go. And then Levi, will you time me as we go? Okay, awesome. All right, here we go. 3, 2, 1, go.
1, 2, 3, 4, 5.
Okay, 5 seconds. 5 seconds to get across my office. Whew. And it's about, I don't know, 20 feet across. So I went about 40 feet in 5 seconds. Now, how far do you think light went in that time? Light traveled about 1,000,000 miles in that time that it took me to go across the room and back. If it took you, when you're running across your room, if it only took you 1 second, then light would have gone 200,000 miles. If it took you 2 seconds, then light would have gone 400,000 miles. If it took you 3 seconds, 600,000 miles. If you, like me, took 5 seconds to run across your room and back, light went nearly 1,000,000 miles. 930,000 miles to be exact, but almost 1,000,000 miles, which is so far because light moves so fast. It is far, but it's actually not even halfway to Mars. 1,000,000 miles is not even halfway to the closest planet to us. So light is really, really fast, but it still takes time to travel. It cannot get anywhere instantaneously. That's interesting. Light is not instantaneous, even though we seem to see lightning immediately. So here are some interesting facts about the fact that light takes time to travel. So if a little ray of light were to leave the sun right now, like woo, and shine toward us and toward our eyes, it would not get here to Earth and to where we can see it for another 500 seconds. That's how far away the sun is. So yeah, if light left the sun right now, it would only get to us about 8 minutes later. And if I turned on a flashlight from here or a laser from here and I shot it at Pluto, how long do you think it would take for light to reach Pluto, which is way, way at the end of our solar system? It would take about 5.5 hours. That's a long time. That's how far away Pluto is. So what that means is that when you look at the sun, you're actually seeing what the sun looked like about 8 minutes ago in the past, which is so cool. Think about that. So the light gets emitted from the sun and then it reaches us 8 minutes later. So by the time we see it, we're seeing the sun in the past. So when you look at, your dog or your cat, you're not like seeing the cat in your eye. You can't get the cat in your eye. What you're seeing is actually light bouncing off the cat, and that's what goes into your eye. But that light, like we just talked about, it takes time to get to you. And since that light takes time to get, it's not very much time, from here to here is not very much time. Like the sun takes 8 minutes, but here to here is not very much time. But what that means is that you're actually never seeing your cat or your brother or your sister or your dog or your friend. You're never seeing them at exactly the same time as they're there. That's crazy. You're always seeing them a little bit in the past. So that's kind of like you're always seeing them as a time machine. You're always seeing it in the past. What that also means is that we have an amazing opportunity to learn about the past, because if you think about this, if we look up into the night sky, now imagine you're outside, it's a super clear night, there's no clouds, no light pollution or anything like that. And you maybe see a really, really faint star up there that's maybe 1,000,000,000,000,000 miles away. Then light from that star left a long, long time ago. So when it gets to your eye, you're seeing that star back in time. And you're seeing it a lot further back than the cat that's next to you. Because with the cat next to you, it took only about a microsecond, for less than a microsecond, for the light to get to you from the cat. But light from some far away stars can take maybe 10 billion years. Billion with a B, 10 billion years. 10 billion years ago, that's like the earliest days of the universe. Actually, there weren't even days in the early universe that long ago, because there was no sun yet. And so there was no Earth to rotate and have days, which is crazy to think about, but you get what I'm saying. Even though there weren't days yet, it was still a long time ago. And the farthest galaxy that we've ever seen took about 13.4 billion years for its light to get to us. It's this galaxy we saw called GNZ 11. You should be seeing a picture of it right now. It just looks kind of like a blob to us because it's so far away and light took so long to get to us that it's just a little bit fuzzy. But 13.4 billion years, that's actually pretty shortly after the beginning of the universe, or the Big Bang, as you might have heard it called, because the Big Bang happens to be about 13.8 billion years ago. So this galaxy formed shortly after that. And crazy fact, this galaxy, GNZ 11, probably doesn't even exist anymore now in our time. Yes, we're seeing it, but since the light was sent to us, the galaxy, its stars have probably exploded or burned out, or maybe the entire galaxy was swallowed by another galaxy, or they collided or something like that. So the galaxy probably doesn't even exist, even though we're seeing it now. That's totally crazy. It's amazing. So the universe can be used like a time machine because light takes time to travel to us. That's so cool. It's just light is way faster than we could ever travel, which means that everything that you've looked at or you're seeing is ever so slightly in the past, just a little bit in the past. And then that's a little longer in the past. And that's a little longer in the past. Or, you look up into the night sky and you are looking way into the past. And that is pretty cool. So the next question I have is about how far back we can see. How far back in our universe time machine can we see? So here's another question for you that I want you guys to go ahead and type in. My question is, how do we know how far away stars are? Look up at the sky, we see a star. How can we figure out how far away that star is? I'm gonna wait. Oh, I've got some answers coming in. So one, can you use a ruler? Smart. You measure distance with ruler. Lasers. I like that, just lasers. Send light to them and see it bounce back. Ooh, I like that one. Google it. Clever, but what if we don't know yet? How do we figure it out? By how bright the star is. If it's dim, yeah, I like that. There's some about brightness. We measure the light and see how long it took. Okay, really, really cool. I like these answers. These are great. So we know that stars are really far away. I'm sure you know that stars they're not right next door to us. They're really, really far away. But they're so far that we could never actually go visit any of the stars. The tools that we use to measure distances on Earth, we can't take them to stars. So it's really, really tricky to figure out how far away the stars are because you can't just, get in your car and drive to Proxima Centauri, which is actually the closest star to us, and take along your GPS to measure it. We can't do that. So there's a method that we use that you can actually see with your eyes, and I want you to try it with me. So all you need for this is a pen or a laser pointer, or your finger even works for this. So this is one of the techniques that we use to figure out how far away stars are. Okay, put the pen or your finger near, I gave you guys enough time to grab it. Put the pen or your finger close to your eyes, and then I want you to close one eye, like your left eye, and see the pen, and then close your right eye and open back up the other one. And so you'll close your eyes back and forth and look at the pen, and it should be jumping back and forth in front of your eyes. You guys seeing that? Yep. Okay. Now, if you hold it further away and you do the same thing, like maybe arm's length further away and do the same thing, you should see it jumping back and forth, but you should see it jumping back and forth less. You see that? So it jumps back and forth a lot more here and then a lot less over here. Yeah, cool. So amazingly, we use this same idea to figure out how far away some stars are. If they're further away, then they appear to jump less as we move. But it's not quite the same because you can't just close one eye. You can try this next time you're looking outside at the stars. You can close an eye and look back and forth, and you won't really see the star jumping back and forth. But instead, we can, maybe move our head a little bit more. And if you do that, then you'll notice, maybe things on your desk move more than things that are further away. And if you move even more than your head does, like imagine if you could move the entire Earth. Well, the Earth does move. The Earth orbits around the sun. So now imagine this, instead of going from the distance of one eye to the other eye, imagine you're looking at a star and going the distance from one side of the sun all the way around in orbit to the other side of the sun. Now you're jumping a really, really long distance, and you can see how the stars jump back and forth. So stars that are closer to us will appear to move more than the stars that are further away. That it works just like the pen. This is something called parallax. Parallax. And I think I saw one of you guys actually write that answer, maybe a couple. So parallax is that something closer to you appears to jump more when you see it out of different eyes, or when you move your head, or when you move the entire planet. And astronomers, to sort of conclude this whole section, astronomers sometimes use that same idea of parallax to determine how far away a star is. And there are actually a few other ways that some of you got. We do look at the brightness of stars. Obviously, the dimmer they are, the further away they are. We do look at how red the light is coming from the stars. That's a whole other can of worms. It's the more complicated version. But for some nearby stars, we get a more accurate measurement by looking through parallax. So now you know what astronomers do. So some of you might still be in, elementary school, but you now know one of the tools that astronomers, like real life scientists, use to figure out how far away stars are. Now, the next thing that I want to talk about is, as we're looking up into the sky and we're thinking about stars and looking at stars, I want to tell you how you are a superstar. You are a superstar. Okay, to do that, I need you to answer one more question. The question for you is, what elements make up most of your body? And some of you may not have heard the word element before, which is totally fine. This is a word you don't really get to until you're in, maybe middle school or high school and taking chemistry. But think of the stuff that makes up your body. Like think of maybe some of the chemicals or anything you've ever heard that make up your hair and your spit and your bones and your organs and things like that. I'm seeing a couple answers come in for water. Yep. I'm seeing some oxygen, hydrogen, some iron, some carbon. Yep, these are all good. Muscle. Yeah, that's one of the things that makes us up. Okay, awesome. These are good answers. Great. So you all did really well. So we know, I think a lot of you know, because you probably drink water on a daily basis, that a lot of our bodies is made up of water. The body is largely made up of water, which, do you guys know the chemical formula for water? I know some of you are probably yelling at your screen, but water is H2O. So 2 hydrogens and 1 oxygen. But actually we're made of more oxygen than hydrogen, even though it's 2 hydrogens for every oxygen. And that's because hydrogen is the lightest element, the lightest one. Oxygen is actually much heavier than hydrogen. So if someone ever asks you what you are made of, what your body is made of, you can tell them that you are about 65% oxygen, 18% carbon, 10% hydrogen, and 3% nitrogen, and then small amounts of a lot of the other atoms. I have this fun little periodic table, and if you guys have ever seen one of these, or maybe one day when you take chemistry, or if you've already taken chemistry, for some of you guys, then we've got hydrogen and helium, and then we've got some of the heavier elements down here. But we've got a few different ones. There's definitely some zinc that is in your body, and yeah. So you're made up of mostly nitrogen, hydrogen, carbon, and oxygen. And then there's a lot of small amounts of a bunch of other little atoms, the heavier stuff like There's like calcium and iron in your bones, and there's potassium and sodium in your muscles and stuff. But get this. When we look at the early universe, so we talked all about how we look into the past and we look at light from the stuff in the early universe. When we look at that light, it tells us that the only elements that were around were hydrogen and helium, just those two lightest elements. But you are made up of oxygen and carbon and nitrogen and a bunch of the other heavier stuff. So the question is, if we only had hydrogen, oxygen, or hydrogen and helium in the beginning of the universe, then where did all of those other elements come from? Those other elements were created later on in the universe, and it's amazing how they were created from giant explosions, but I'm going to explain. Okay, I promised also that a rainbow would come up at some point. I'm going to put my periodic table back. I promised a rainbow would come up at some point in this. So how is a rainbow made? This is a rainbow of notebooks, but you know, a rainbow in the sky. Usually it's raining when we get a rainbow, but light from the sun shines down and it gets spread out and we see these beautiful colors. And I can show you that by showing you, I'm gonna run over here and show you the lights that we're using in the studio right now. So this is our sun. Can you guys see this? Is that okay? So you can tell that the light we're using in the studio here is like a white light, kind of like the sun, you know, a little bit whitish yellow. But then if I grab something like a CD and I hold it close to the screen over here, you can see a bunch of different colors, bunch of different colors mixed together. And sometimes I've also got this prism, which, well, every once in a while works. I don't know if it's probably easier if we just, you know, prism split up light, but it's probably easier to just see in the CD. Light is bouncing off of my lights here, my studio lights, and hitting this CD and splitting up into all the colors. It's spreading out like a rainbow. And so what that tells us, thank you, Levi, so much for, for keeping the focus good. What that tells you, light spreading out in the different colors, tells us that sunlight, or, you know, our studio lights, which just look like they're sort of a bright yellow, white color, are actually a bunch of different colors from the rainbow mixed together. And stars, like the stars that we look up into the sky, those should also have all of the colors. So if we took the light from a star, we split it up with a prism or with a CD, something that sort of splits up the colors, the light into rainbow colors, then we should have all of the colors, all of them. So when we look at light from stars, we should see all the colors just like we do when we look at the sun. But something really strange happened the first time that scientists looked at stars. When they spread out the light from stars into rainbows, there were actually colors missing. So if we could go back to that picture that was up with the prism and then the spectrum on the bottom there. Yeah, you see maybe some little black lines. Those are colors missing. So take a look at that spectrum. You've got like a line in the red, meaning that the red is missing, and then one in the green, one in the blue. So when scientists looked at this spectrum, at the rainbow colors, they were like, why are there colors missing? And they figured out later that different elements in stars, we're talking about the elements that make you up, like oxygen and hydrogen and helium, different elements absorb different colors. So stars are typically made up of a lot of hydrogen and helium and some other stuff. Helium, you know, is the stuff that's in balloons that makes your voice go up. And hydrogen obviously is the stuff in water. So hydrogen absorbs some of the colors and leaves that black line or a black little dip in the rainbow. So we get a little bit of that red missing. And helium absorbs a different color. So it makes a different line. So if we look at how dark those lines are or how much the dip is, then we can figure out how much hydrogen and helium and oxygen and carbon and other elements are in the star. That's so amazing. We can look at a star, we can look at that spectrum, and we can tell how much of each element is in the star just by looking at the light. So if we only see, let's pause on that. That's pretty cool. We just look at the light and we split it up into a rainbow like this CD does, and we can tell what the star is made of. That's amazing. So now when scientists looked at the oldest stars, they looked at the ones that are furthest away, they found that they only really saw hydrogen and helium, as we talked about on our little periodic table. That means that there was only hydrogen and helium at the beginning of the universe. Those are the only elements around, only hydrogen and helium. So then where did the heavier elements come from? The ones that are in your body, like zinc and iodine. I know some of you are probably yelling, fusion, fusion at your screen. And you are right. Some of the heavy elements are made in the center of a star where lighter elements like hydrogen and helium are fused together. But there's another way that really heavy elements are made. Check this out. This is a fun little demo that I would love for you to try at home. But if you don't have the materials right now, then you're going to have to try it later. I'm going to need Levi for this one. So he's going to come on up here. So what I have is a basketball and a tennis ball. It's a pretty flat basketball, but imagine it bounced better. I've got a basketball and a tennis ball. And what I'm going to do is balance the tennis ball on top of the basketball, and then we're going to drop them together on the count of 3. And I want you guys to guess what you think is going to happen. Do you think that the basketball is going to bounce higher or the tennis ball? Ready? Okay, 1, 2, 3. Okay, I hit Levi. We're going to try it again because we got to balance it a little bit more straight. This is going to be your challenge when you guys try this at home, is getting it to balance perfectly straight. Okay, ready? 3, 2, 1. Woo! Yes! All right, so my basketball barely bounced at all because it's very flat, but my tennis ball flew up and hit the clouds. So I think that's a good metaphor. So what happened here? This really heavy basketball transferred a lot of its energy to this lighter tennis ball. And this is kind of like what happens when a star collapses. Yep. Massive stars can sometimes collapse when they run out of fuel, like when they can't fuse anymore, they can't do fusion anymore in the center. They run out of fuel and they collapse down, which is kind of like the basketball falling and hitting the ground. It's like collapsing. Now, the heavier elements in the center will hit and rocket the lighter elements outward. So if you ever see a picture that looks like a exploded sort of, I don't know, weird cloud or something like that, that's usually what comes after a supernova is, yeah, something like this. That's like the stuff that rocketed out. But what happens in the center of the supernova is these really heavy elements come down and they collapse and they fuse together in this really violent, really, really energetic collision, and they make super, super heavy elements. And then, it all bounces out and gets shot out into the universe. And then other stars are made from that, and it shoots those heavy elements everywhere. So the conclusion of all that, well, first, the conclusion is that you guys should definitely try this at home if you've never done it before. The conclusion of that is that some of the material that made up our bodies, came from supernovas. So when you're out there and you're thinking about, stars and where you came from, some of what you're made of came from the exploding innards of a massive star. And we actually know that the bigger a star is, the faster it burns into a supernova, and the smaller it is, the longer it burns. And our sun is about 4.6 billion years old. Stars like our sun live for about 10 billion years. So in order for there to have been a star that formed and exploded into a supernova and shot its innards into space, and then we formed from that here on Earth and in our sun, that star had to be much, much bigger than our sun. Significantly bigger than our own star. So that means your family tree dates back to a really, really old, really massive star. That's so cool. So in conclusion to this section, we can split starlight into different colors. like the CD does. And then based off of which colors we see, we can tell what elements are the star is made of. And then the oldest stars don't contain the elements that we do that are in our bodies. So parts of us came from exploding supernova stars. That's cool. So you are a superstar. And I hope that that's all the proof you need, that you're made from ancient star stuff. That is pretty amazing. So it's fascinating. So cool. Now our final section, I thought it'd be really fun to do some more questions. I've got some fascinating questions as you sit there mind blown that a lot of your body or a lot of the things that made you up came from the center of stars that exploded and shot their innards outward. As you think about that, I've got some more fun questions, and I want to call this section, have you ever looked up and wondered? A lot of fun questions here. So let's get started on these ones. My first question is, when stars first form, is their material A, hot, B, cold, or C, room temperature? So when a star first forms, the material that it forms from, does it collect together and is it really hot, or does it start out cold, or does it start out sort of room temperature? Seeing a couple different answers coming in. Yep, a little mix, okay. A lot of you are saying A for hot. So you think that, yeah, that makes sense. Stars are hot. The answer is actually cold. B, cold. So if you got that, you got it right. Stars mostly form from frozen hydrogen that gets pulled in by gravity. And then the hydrogen starts colliding and heats up the star until it's glowing hot, literally glowing. It gets so hot, it starts fusion in the center and it starts to glow. Amazing. The next question is, what stars live longest? Between these two, A, the biggest stars, or B, the smallest stars? Which do you think live the longest? The stars that are big or the stars that are small? Which ones have the longest life? I'm seeing a couple A's and B's so far. Yep, but I think it seems like I'm mostly seeing that the biggest stars live the longest. That seems like it would make sense, right? You've got a bigger star, there's more stuff to burn through, more fuel, more fusion. But the answer is actually, the smaller the star, the longer it lives. Yep, I know. A lot of this stuff in astronomy is so counterintuitive. Bigger stars actually create so much energy that they burn out even quicker. So they burn really bright, but really fast. So on average, smaller stars like our sun pace themselves. And that means that a lot of the available matter that came to us from massive stars happened because they formed and then they burned and then they exploded and then they reformed into things like our solar system with our planets and our sun. Yep. Pretty cool. Next question. Do most stars exist in A, groups of 2 or more, or B, do they exist on their own far away from other stars? Do you guys think that most stars are in little groups of 2 or more stars, or do you think they're usually on their own, like our star, the sun, that's far away from any other stars? Really far, light years away. Okay, I'm seeing a good mix here. Some of you think that stars are usually in groups. Some of you think that they're on their own. Awesome. Okay, the answer is actually kind of surprising to me, although it seems like some of you got this. Most stars are in binary systems. Bi means 2, so binary systems means 2 stars or larger. Sometimes there are 3 stars. And I think some of you were probably thinking of galaxies where there's a lot of stars together, and that is true. Although sometimes there are stars that are between galaxies, and sometimes that happens. A star can be between a galaxy if, imagine this, a supermassive black hole came through a galaxy and stole a star away and carried it to the space between galaxies. That can happen. Sometimes galaxies collide and they rip stars off of each other and they leave the stars sprinkled throughout the universe. So that can happen, which is amazing. Very cool. Stars do crazy things. The universe does crazy things. Next question. Which of these is true? A, most stars have planets orbiting them. Or B, only a few stars have planets orbiting them. So obviously our sun it's a star. It has planets orbiting it. It's got our planet Earth, and it's got Mercury and Jupiter and Venus and a bunch of different planets. Which of these is true? I'm seeing a couple different answers, but I think I'm mostly seeing that most stars have planets orbiting them. Awesome. You guys are actually, pretty on the right track. Because the answer is that the vast majority of stars do have planets around them, which is really cool to think that most stars are not alone. They mostly have planets orbiting around them, and a lot of planets. So yeah, that's really cool. And it's looking more and more likely that most stars or a lot of stars have planets that are the perfect distance away for life to form. Potentially, we call that the Goldilocks zone, where the star is just the right distance away from the planet that the planet can start to form life. Earth is obviously in the Goldilocks zone for where life could form on Earth near the sun. Amazing. Just 2 more questions here. These are fun. Okay. Are there more A, stars in the universe, or B, grains of sand on Earth? What do you guys think? Do you think, looking out of the sky, seeing all those speckles across the sky, are there more stars? Or now imagine all the beaches on the entire planet. Are there more grains of sand? And also all of the deserts. Imagine all the grains of sand in the desert as well. I'm seeing a couple different answers. There's A's and B's. Yeah, pretty split on this one as well. The answer is that there are more stars in the universe. So the answer was A. There are more stars in the universe. That to me is totally nuts, because you think of all of the beaches and all the grains of sand, how small they are. Like, you would never be able to count all those. But the universe is so big that there are more stars. That's incredible. And last question here on our speed round. Last question for you guys. With today's fastest rockets, how long would it take to get to the nearest star past our sun? So imagine you got in the fastest rocket that we have on Earth and traveled all the way to the nearest star, which is, I believe, Proxima Centauri. How long would it take us? Would it be A, 70 years, B, 700 years, C, 7,000 years, or D, 70,000 years? What do you guys think? All of those are a longer trip than I would ever want to take in a single rocket. So that trip is not for me. But the answer is actually D. If you put D, you are totally right. The answer is that it would take 70,000 years to get to the nearest star. Oh my God. We would all be long gone. Some of our ancestors would maybe hopefully be, getting on that rocket. Maybe rockets would be a lot faster by then, but 70,000 years. That's why we have to do so much of our learning about the universe from so far away, just by looking and observing, because it takes so long to get to any star. We've never gone to any other star. We've never gone to our own sun, because it's hot. But the cool thing is that we can look way back into the early universe, even back into I didn't show you guys this yet, but the beginning of the universe. This is actually a picture we have of what the very, very early universe looked like. That's pretty lucky, if you ask me, that it just so happens the way light travels, we can look back in time. And we can learn all kinds of things by looking into the past. What can we learn? What can we learn from looking at the oldest stars in the universe? Well, we can better understand the origin of our universe. Where did we come from? And it gets complicated as we start looking back, because here's some fascinating things. Remember how we talked about parallax and closing your eyes back and forth? We can't use that for really, really far away stars that are really old. We can only use that for up to about 300 light years away. And that's not even halfway across our galaxy. That's not even halfway across the Milky Way galaxy. So there's all kinds of exciting research trying to learn about the stuff nearby us. There's a really cool mission called Gaia. You should look that one up. That's sending a probe out to map the galaxy that we have, our Milky Way galaxy, in 3D. And it's going to show us up to 30,000 light years away. And then we have other kinds of maps we're making of different stars. And when we look at the stars and the galaxies and we map them, we can figure out things like how the universe is expanding and growing, which it is. That's another amazing fact. The universe is expanding. We can maybe think about what will eventually happen to the universe. We know that it started out a lot more tightly packed together and now it's expanding. What's going to happen in the future? We can figure out, how did the first stars form? You know, we look at galaxies that are adult galaxies in the sky, but we want to know how baby galaxies formed. What did they look like? So looking back at the oldest stars in the sky is sort of, you know, filling in the family album of stars and helping us figure out, you know, where we are, where we came from, all the stuff that makes us up. Where did it come from? And all this research is still ongoing. Stars are beautiful and fascinating, and they tell us so much. I think that they are one of the best ways to learn about the universe. And they fascinate me every day. So I hope you guys enjoyed my lesson about stars. That's about all I got for you about stars, stars exploding, you being a superstar. That's it. I hope you enjoyed.
That was amazing. Thank you so much. I will be running around telling everyone that I am made of supernova dust. You know, not just the rest of this week, the rest of my life. That's really amazing. Hey, thanks to all of you out there. You guys have some amazing questions. We're about to get some of those answered, so keep those coming. But remember, at the beginning, I told you if you had a camera ready, we'd give you an opportunity to be the stars of the show, lean in and get a selfie with Dianna, and some cool prizes that we'll talk about. The cat there, and if you upload it to Instagram, tag the physics girl and Varsity Tutors, you'll be able to win a spot in one of the after school clubs with Varsity Tutors. Highly recommend Cosmic Adventure Club to learn more about stars, or Curious World STEM Club to do some more hands-on science experiments like Dianna was showing us here, and that cat there, which we will describe in a little more detail there for you as well. I think that gives everybody enough time to get those cameras ready. So Dianna, we're going back full screen to you, and let's get those pictures.
Yeah, that's great. Yeah, we zoomed in a little bit more for you guys. Posing with the cat, I'll just... I wish I could see you guys. Hold up your cats, your stars, your prisms. Whatever you guys have there at home.
Thanks, everybody. You heard her. She said she wishes she could see everybody. The best way to make that happen, get those pictures up on Instagram, tag Dianna's Physics Girl account, and Varsity Tutors. Again, we'll have those rules up on the screen, or official handles up on the screen, for you to know exactly who to tag, and you'll be entered to win that prize package. And we hope that you do. Now we got to get some of your questions answered really quickly. We can. We've been hyping this prize. Can you tell us a little bit about Schrodinger's cat? I think that's such a cool prize. We want to make sure everybody knows how cool and clever that is.
Yes, we actually, so this is Schrodinger's cat, which is our little adorable representation of a whole other type of science. We talked about stars and the biggest stuff in the universe today, but this is a cat referring to quantum physics, which is the physics of the smallest, tiniest stuff. And Schrodinger's cat was this little experiment that Schrodinger thought up of about a cat being sort of a state of alive and dead. So we made Schrodinger's cat where it's dead on one side and alive on the other side. We worked for way too long, like a year and a half on making these, and they're finally here. So we'll have a couple of those for you guys.
Yeah, that one's so cool. It's where quantum physics meets philosophy and all those. It's the lucky winner who gets that, and a spot in one of these clubs is great. And so yeah, get those pictures up there. All right, you guys have had some other really good ones. One of my favorites. Thank you for asking this. I think this one may be hard. What is it that makes light travel so fast? You know, we know light travels way faster than sound. Obviously, a little faster than you can run back and forth across your room. What makes light travel so fast?
Oh my gosh. If we knew the answer to that, we would have unlocked even more secrets of the universe. But this is one of those questions that has a pretty unsatisfying answer, which is just that that's how our universe works. It's just like one of the laws of the universe. Like, why is the charge of an electron what it is? Why is the size of a helium atom what it is? It's just sort of what we were given with our universe. And scientists have thought of different universes that have different laws of physics and maybe a different speed of light. But in our universe, that's just sort of what we were given.
Nice. Okay, it leads to a follow-up question. do you think we'll ever be able to travel faster than that, as fast as that? Or in your opinion, that's one of those, it's a hard question, but what do you think? Do you think we'll ever get there?
Oh, unfortunately, I have to answer as a physicist, which is no, I don't think we'll ever be able to go faster than light or even go the speed of light, because crazy things happen when you get up to the speed of light or you approach the speed of light. You end up having to give it, like, you know, you got to press on the gas to accelerate, but you would have to press on infinite gas. So you have to have like an infinite gas pedal in order to get up to the speed of light, as we understand the laws of physics now. So unless some crazy groundbreaking discovery happens, or unless the laws of physics change, then unfortunately, no, we'll never even be able to get up to the speed of light. Just as you go faster and faster, it actually gets harder and harder to go faster. So that's one of the limits. It really, truly is a limit.
All right, you heard it. There's a challenge out there. We challenge you to find a way. We know it's going to be difficult, but no, that makes
spend too much
sense.
Time.
Hey, one of my other favorites was, say we were in one of those other galaxies or solar systems, and we were able to look back at the Earth.
Mm-hmm.
Would we be seeing the Earth as it was in the past? That stands to reason, right?
Yes, absolutely. It goes two ways. So if you're in a galaxy that's, say, 1 billion light years away, and it stays 1 billion light years away that whole time, then you would see the Earth as it was 1 billion years ago. So same exact thing, which, you know, humans wouldn't be alive. So if there's a star that's that far away, you'd be looking at a very different Earth and a very different planet than the one we know today, which is kind of cool. Yeah, that's a great question.
That's going to be the idea of time travel. If we found a way to send light out and then back, maybe we'd be able to see a reflection of ourselves in the past somehow. So
yeah. I mean, it's kind of what we do. We look at pictures.
It's a good
Time
point,
travel,
actually.
unfortunately, only really shows us the past, as we know. We can't look into the future yet, but yeah, we at least can see into the past.
Yeah, no, that is okay. And speaking of looking all the way back into the past, one of my other favorites was, you know, we saw that we're pretty close to being able to see all the way back to the Big Bang. We saw that, you know, 13.4 billion years ago. Do you think it's possible to see all the way back, to even see how everything started? Do you think we'll get any closer to it? Do you think we can get all the way there?
So a crazy thing happened. I showed you guys this at the very end, and I didn't really talk much about what this was, but this is actually a picture of very shortly after the Big Bang. Something happened where there's a sort of, you can imagine the Earth almost as this, or the universe, there was no Earth yet. You can imagine the universe almost as this soup, but you couldn't see through it. So it's like imagine you're in like really murky water and you're looking out and you can't see anything. And then all of a sudden the water clears up. So that's a metaphor. That's sort of what happened, you know, a few 100 million years after the Big Bang, or is maybe a few, I don't remember exactly how many, but it wasn't shortly after the Big Bang. It was, I mean, on a cosmic scale, it was shortly. These things are the scales of the universe. Oh my gosh, they make your brain hurt. But shortly after the Big Bang, the universe cleared up, and then we suddenly got this picture. So this is the light that started traveling from all the way back in time when that universe cleared up and the murky water of the universe became clear. But before that, no light could really get through and get across the universe. And since right now, light is how we see most of the things in the universe, then we can't see before that time when it became clearer. So this is a really interesting question. If you want to know more, you should Google something called the cosmic microwave background. That's what this is. It didn't have a smiley face. That was sewed onto this little pillow, but it did look about like this.
That's amazing. Cosmic microwave background.
Cosmic microwave background. It's like
excellent. Well, I'll be checking that out for sure.
Yeah.
Hey, last question for you from, just pure enthusiasm from everybody out here. You have such a cool job. This is what you do, is get to talk about cool science topics, research them, learn more about them. So everyone that's enjoying themselves today is asking themselves, hey, how do I become more like Dianna? What's your advice for people either inspired by today or who have been inspired before and are just thoroughly enjoying today. What can people do who really enjoy looking back in time, thinking about, the earliest stars and the implications for us and all those? How do we get to be like you, or just further that passion a little bit more that you ignited in so many people today?
Well, I'm a YouTuber now. That's mostly what I do. Or some people call me a teacher, but I'm certainly not in the classroom. Shout out to all the teachers out there who really do the good thing. But I started out as a scientist. I went and got a degree in physics. So I went and studied science, and I did some research in something called particle physics. I was looking for something called dark matter and looking at neutrons and all these little particles that make us up. And then I went on and did astrophysics research. So I really was researching the oldest stars in the universe. A lot of what I talked about today was based off of what I learned when I was doing research as a scientist. And then little by little, I also simultaneously, I had an interest in art and in photography and video and making fun things that could communicate this stuff as well. So I did that at the same time. And I think that's how you eventually end up doing something like making a YouTube channel on a passion. Like first you pursue the passion, which for me was science and physics and wanting to learn about the universe. And then I learned another skill, which was making videos and photography at the same time, and eventually combined those two things to be able to tell stories about the stuff that scientists know and I got to learn, and the stuff that we're still learning. So yeah. Lots of different, expose yourself to lots of different things and then combine them together.
Awesome. Well, we're so glad you did all that for today and for all the amazing content on your channel and all those kind of things. So thank you for taking the path you did to bring us all together today. And I think the lesson for everybody out there, just never stop learning, always stay curious and learning new things. And that's how you get to do cool things and have all kinds of exciting experiences. So Dianna, thank you so much. This was a blast. We got some experiments that we were able to do along with you that we can do at home. The ball one, especially, I think you've mentioned you've got it one where you do it with 3, and it can really make sure you've got some supervision because we even saw that tennis ball get out of hand. We've got some cool things to practice with, lots of new information to wow our friends with. So can't thank you enough. For everybody out there, all of your questions were absolutely amazing. Participation was great. It was so fun to see the chat just overflowing, the polls overflowing and everything. So thanks to all of you out there. Reminder, I'll get those instructions up here so you guys have those for the way out. You've got an opportunity to win a spot in one of our after school clubs, plus that cool Schrodinger's cat. So make sure you do that. If you don't win, you're more than welcome in these clubs as well. There's some information on your screen to be able to learn a little bit more about it. We'd love to see everybody back here soon. Dan, I think you'll be back a little bit later in the fall, and everybody else, we hope to see you even sooner than that. So thanks to all of you, and have a great night, everybody.
Amazing. Yeah, thank you so much.